see the next. We now move on to rotor acoustics. And the next presentation is by Dr. John Prieur. He's from ONERA, and the title of his presentation is Helicopter Rotor Aeroacoustic Research at ONERA.
Okay, thanks a lot. I will be presenting to you some aspects of the research that we have been conducting at ONERA in the field of helicopter rotor acoustics. As you know, there is a need from industry to have numerical prediction codes to help design of low noise and low rotor and helicopter concepts, and also low noise flight procedures. So to do this, we have been working in parallel in several directions. First, we have been developing noise prediction codes based on integral methods, and for example, this method is the classical and also the permeable surface formulation is the first one we are using, and which is in fact very well suited to helicopter rotor problems. And we have been working at understanding the physical mechanisms involved in noise generation, and that is that we have developed dynamic and aerodynamic prediction codes to provide input data to the acoustic codes. And last but not least, we apply these codes to the study of noise reduction concept. I will just talk to you about some problems that we have encountered in implementing integral methods for helicopter rotors. When you implement the integral methods, you choose a control surface, and you have to vary this control surface until you achieve stable results. And you can choose either a control surface which is moving with the body, like it could be the blade surface itself. It could be a gridded surface surrounding the body, which is then moving in the observer frame. It could be also a fixed surface of revolution on which rotates a grid, which is then moving in the observer frame, the fixed observer frame. And in fact, in certain cases, where you have shock delocalization, that is forward flat BVI and also high-speed impulsive noise, then you are obliged to extend the control surface beyond the sonic surface. And then it happens that some grid cells can be supersonic in the direction of the observer. So the integration can become tricky. What is the status of existing methods for this to tackle this problem? The methods for the classical subsonic cases, in fact, they discretize the control surface in acoustically compact source elements, that is, source elements of size small enough compared to the observed wavelengths of the sound. And of course, numerical singularity is encountered when grid cell Mach number relative to the observer is close to 1. But there are alternative methods like the method designed by Ken Brentner, which avoid this singularity by building the so-called acoustic source domain or a retarded source domain. But they have to do this for every observer location and reception instance. And to do this, they need to starting from the CFD grid to refine the grid and interpolate, and also because of the rapid changes with time of the shape and the topology of this retarded surface, small time steps must be used. So there is a potential CPU problem if calculations at thousands of observer locations for noise simulations or ground noise carpets computations have to be computed. And we have to, in fact, because of the changing, of the high directivity of helicopter noise, rotor noise, and which is changing with the flight conditions, we need to calculate each time the noise for a great number of locations. Because you don't know where the maximum noise is. And we have found a solution. We have proposed a solution to obviate these drawbacks, and we have developed an integration method, which is called the method KIM, because it was originally for Kirchhoff. And the main features of this method are that we start from the calculation from emission time and proceeds forward in time. So that no acoustic domain construction or retarded time calculation is required. But which is more interesting is that each grid cell is treated as non-compact. That is, we have no longer Doppler singularity, and the CFD grid itself can be used as integration grid. And furthermore, the integration method follows the CFD grid elements and sums its radiation in time, so that relatively large acoustic time steps, for instance, for the helicopter problems, the rotor rotates at a low frequency, so the input data vary essentially at low frequency, so that we need not very small time steps. Maybe the period divided by 64 is enough. And so low computer resource consumption is obtained, and the method is implemented without modification with a deformable CFD grid. Just a principle of the method, a very basic principle. Let us consider a control surface element, which I've called delta SI. And this is the observer X, the distance R between the surface and the observer. Let us call G the difference between the emission time tau, the reception time T at X, plus the distance divided by the speed of sound. And in fact, in the classical approach for the subsonic case, the acoustic pressure is calculated as this, this integral. That is, that the source element is treated as a point source, which is carrying the integrated strength over delta SI. And you recognize the classical R3 Green's function here with the delta function. And in fact, what we do is to account from the fact that signals emitted by this side of the element arrives earlier than a signal emitted from this side, and so that the complete signals arrive in a certain duration of time, which is featured here. And basically what we do is that we replace the delta function by a Crinell function. We spread basically the acoustics over a certain higher pointer. Okay, thanks. Okay. And here it's a very simple configuration, but we have shown in earlier papers that even if the source element is not built so simply, we can use the same Crinell function, but it is then an approximation. But it works very well. to show you a schematic of this time integration. In fact, what we do to calculate the pressure, the acoustic pressure generated by this, associated by this control surface element, we calculate this integral, and let us call pi I this integrand here. And you recognize that this quantity is just simply the ratio of this quantity, which is the acoustic pressure that would be radiated by a compact source element, divided by a delta t, which is a reception time interval at the observer location for the signal emitted at time tau by this element. So that this quantity, pi I, could be called time rate of acoustic pressure. It's not a good name, but. And just to figure out what this integral is, if you were plotting by mind a diagram like this with pi I in ordinate, with the emission time here, with the reception time here, when you follow control surface elements, the Crinal function associated to this element describes a volume here. And this integral is simply the area of this volume cut by a plane at time t. This is an example of results that we obtained with this, using this method. This is a simulation of helicopter rotor. It was a two-bladed helicopter rotor tested in an ONERA wind tunnel in forward flight with wind tunnel velocity arriving from the left here. And you can see here that you have an attached shock here, which is, after weakening, give birth to a shock-like sound wave, which is radiating upstream. And the control surface is this half of the cylinder here. And we have used about 4,000 observer locations for this unsteady calculation. And we need less than 1 hour of computing of time on a PC. Some kind of thing we can derive complete noise directivity surfaces like this using several thousand of observer locations. And you have here a correlation with experiment for in this wind tunnel case, which is not too bad. The input data have been provided by CPD code ONERA. For PVI, it's not the same case because, as you know, Euler and Navier-Stokes methods have difficulties at the present time, to capture and preserve and convect without dissipation the vortices between the times they are generated and their interaction with following blades. It requires, for 6-degree descent flight, more than one rotation, which is very long for the CFD calculation. And so we were working in the CFD side, but we didn't want to wait the result of CFD to start calculating. And we have decomposed the complete calculation in several steps for which adapted methods have been developed. And the first step is an iterative calculation between the host code, which computes the trim of the rotor. In fact, it computes the equilibrium of the complete helicopter, but it deduces the trim of the rotor once you want to achieve a given lift and propulsive force, and also calculate the dynamic and the aeroelastic deformation, and iteratively with the free wake vortex lattice method. And the next step is the vortex roll-up model, which, starting from the span-wise blade lift circulation distribution, computes the interacting vortices. The next step is aerodynamic computation. It is the RX code, which is based on the singularity method. And in fact, since the noisiest cases are the very close interaction, even the collision case, and we didn't want to perform Navier-Stokes calculation. So there is in the code a cloud vortex model option in the case of closed PVI. And when the code detects a closed PVI, it changes the model. And the last step is Prieur code, which computes the noise based on Fox-Suknik equation. And this is to validate these computations, we use hard test results. As you probably know, the HART Corporation is a corporation between the US Army Ames, NASA Langley, DLR, and ONERA and DNW. And in these corporations, there were up to now two test campaigns, in which a highly instrumented model of a BO-105 rotor was tested. And the last campaign in 2001, 2002, with extensive PIV measurement for characterization of the vortex velocity field. But the work processing is still ongoing. And this slide shows noise control plots in a plane below the rotor. You have the experiment on the top and the computation with the previous computation chain below. And the two first images correspond to the so-called baseline case. In fact, in this test, the rotor was operated with conventional cyclic pitch variation. This is the so-called baseline case. And also, in these four images, these four images correspond to the addition of the classical cyclic variation to a 4 per wave variation of the blade pitch, which we call higher harmonic control. And by adjusting the phase of this higher harmonic control, we were able either to decrease the noise by 4 to 5 dB, or to completely decrease the vibrations, but unfortunately this was corresponding to the maximum noise with this 4 per wave, but with other frequencies could be different. And as you can see, the comparison is very good in terms of absolute noise level and directivity. We have also some kind of comparison with, in terms of time, signatures of the rotors for the same cases at maximum noise location. But in fact, these tools, we have used these tools for the design of low noise rotor, model rotor. This is the Aeroacoustic Corporation, in which, in close cooperation with DLR, we have numerically designed, built, and tested in DNW at low and medium speed and Modane at high speed, a low noise model rotor. You can see here the shape, the platform shape of this of the blade, and you see on the right the blade that we selected as a reference. It's the 780 rotor, which was at the time a modern rotor with parabolic sweatback leading edge and an hydroll at the tip, and it has a very good performance. The objectives were to decrease BVI noise, and BVI stands for blade vortex interaction. And to achieve this, we wanted to decrease the vortex strength, and to achieve this, we were playing with the blade span-wise lift distribution by modifying the chord span-wise distribution like we did. And we wanted to modify the interaction geometry, that is to avoid any parallelism between vortices and blades. To do this, we introduced a double sweep, forward-backward. And also we played with the quartz fine-wall distribution to have a vortex convection which would be higher in the inner part of the disk than at the tip, to have non-parallelism in the vertical direction. You have the blade like this and the vortex is ideally like this. See? And in addition, we wanted to decrease thickness noise and low frequency loading noise by reduced airfoil thickness, advanced airfoils, and delay shock delocalization using advanced airfoils, and the backwards sweep was beneficial. And all this with minimum performance and vibration penalties. And these are the results that we obtained. At maximum noise descent angle for the nominal weight coefficient of the helicopter, which corresponds to a dolphin helicopter, we got between 3.5 to 5 dBA noise reduction. You can notice that we predicted 8, because in fact we over-predicted the noise of the reference rotor in this case. So our predictions have certainly got the physics, but the numbers were not so good. We got between 5 and 7 dBA noise reduction for other weight coefficient of helicopters, and also significant gain in power for reduction at high speed, but a penalty in hover for at high thrust, and which was not predicted. And also the dynamics 3-per in plane moment was good, but the 4-per vertical force was too high, which was also all under-predicted. And we are using the same tools to work also on active blade design. This figure shows a model blade with an active flap here, 20-inch flaps, which is actuated by a piezoelectric elliptic actuator like this. And this is done in cooperation with DLR. So we design the blade, we manufacture the blade, and we will test it in wind tunnel. And also we have performed a numerical study for a scale 1 ECD rotor based on the same concept. And this rotor should have been tested by the end of this year, but I don't know the results. In fact, the competition chain that I showed you is able to compute the noise in steady flight conditions. That is, flight conditions where the flight path angle is constant and the velocity is constant. But reality is different. And in reality, we have maneuver, and if we want to decrease noise, we can design unsteady flight conditions. So, since in our competition chain, the freeway code was assuming a periodic solution for the rotor, we had to develop a time-marching freeway prediction method. This is the mean code, and you can see here a wake, which was predicted for a maneuver, which is a right turn. And I will show you very briefly the results, the acoustic results corresponding to this maneuver. So, suppose that we start from, I have to say also that the trim of the rotor is computed starting from the computation of the complete equilibrium of the helicopter. We start from a forward flight. You can see that we have, this is a ground noise carpet. We have a certain BVI spot on the ground. The white is a helicopter rotor here, advancing like this. And we perform a right turn, a turn like this, and also, which is important, is that the rotor is rotating in this direction, in this sense. So you start the right turn, and you can see that you have an increase in BVI noise. In fact, this is due to the fact that helicopter rotor is tilted starboard and it's getting closer to its wake. Okay, and surprisingly, the noise decreases. It is due to the fact that as the rotor is tilted starboard, the pilot has to increase the collective to get more thrust to maintain the helicopter in altitude. And so if you increase the thrust, you push the vortices downwards. So there is a way you see the noise. Of course, I must say that there has been no validation up to now of these calculations, which were presented very recently. So, no, that's... okay. This is I will try to go quickly. Also, what we want to reduce the helicopter noise, we have to play with the rotor design, but also you can play with the flight conditions. And one flight condition which is promising is decelerated descent. When you decelerate the helicopter, you tilt the rotor disc backwards. By doing this, the vortices may pass much above the rotor disc and not cross the rotor disc. And you can suppress BVI. And this is what is predicted here. You start from a steady descent. I think it's a 6-degree descent. You have a very high noise, BVI noise here. And you can see that you have completely suppressed the BVI. So I will conclude. Okay, I will not speak about broadband. Okay, just before the conclusion, I have to say that when you modify the flight conditions, you modify also the operating conditions for the tail rotor. And you have to account, in some cases, you have to account for this also in your noise prediction. And one of the tools that we have to assess the participation of the tail rotor is noise source localization, which is similar to that Yoshi presented using phased microphone arrays. Here it's a cross-shaped antenna which is on the ground. And you can see here that we were able to localize depending on flight conditions and quantify the noise from the tail rotor or the main rotor. I conclude now. My conclusion is that I can say that acoustic code based on integral methods are now mature, but dynamic and aerodynamic numerical codes based on physical models provide valuable but not 100% reliable tools, as you have seen, for low noise concepts, and that we would need, at least for reference computations, we will need CSM CFD tools, for instance, for BVI. But the necessary condition is to improve these methods, first to better account for blade aeroelasticity and dynamics, which governs the blade loads, and second, to better capture and convect without dissipation the rotor vortices.
Take one question. Okay. You showed one case where, in the effort to reduce vibrations,
Yes.
to increase noise.
Yes, yes.
Is there an interpretation of that?
The interpretation is not direct and not obvious. No, there is no simple relationship because if you change the frequency of the higher harmonic control, you can have simultaneously vibration reduction and reasonable noise and no increase of noise level. But you have to, for instance, with HHC, you are limited in frequency. For instance, if you acted with a 4 per wave in the fixed frame, this translates in 3 per wave or 5 per wave in the rotating frame. So you are limited in frequency in the rotating frame. So what particularly in the US, but also DLR has implemented is individual blade control. That is, the actuation is in the rotating frame, and then you can actuate with any kind of frequency. And by doing this in flight, DLR obtained a very good result. So it was related to the four-power wave and to the torsional response of, because the torsional, first torsional mode was close to four-power wave.